Thank you. First, I'd like to thank the organizer for organizing this wonderful event and also kindly inviting me to speak here. So this Institute for Advanced Studies is, of course, very special place for all the physicists and also scientists. And yeah, I'm very happy to give some talks here. So as you have already seen the program, the title of my lectures is Applications of Flux Insertions and Large Gauge Invariance. And some of the applications include so-called deep shoot Matisse type theorems. And also Luttinger theorem. Which I think last week Subia mentioned a little bit about this. But maybe these two applications these days were known, and I see that in some schools, in graduate course, some people cover this approach, flux insertion approach to these topics. So I'm afraid some of you already know this stuff very well, maybe even better than I do. But still, these are important and interesting topics. So I will discuss these applications. But I will try to also introduce some maybe lesser known applications like F-sum rule. And cone formula, and also electric, the issue of electric polarization, and so on. Okay, so and let me start from very elementary stuff. That is, if you have some system, and let's say this is x direction. So if this is two-dimensional, the two-dimensional system is defined on xy plane, maybe lattice model or continuum. And then I want to impose periodic boundary condition. So then this system may be identified as a ring embedded in higher dimensional system, higher dimensional space, like this. And yeah, so let's say the system size is, the length of the system is Lx in x direction, Ly in y direction. So once you impose a periodic bound condition, then you can identify the system as a ring or torus or annulus embedded in higher dimensions. Then we can at least imagine introducing a magnetic flux inside this hole. So that this magnetic flux is completely confined in this empty hole. And this magnetic flux does not touch this two-dimensional system. So then if the magnetic flux does not touch this two-dimensional system, then at least classical, in terms of classical mechanics, the particles, okay, so here you have a system and there are many particles, and these particles move around, but the particles on this two-dimensional system never touches this magnetic flux, magnetic field. So as long as you consider static magnetic flux, then classical mechanically, these particles are not affected by this magnetic flux. So this flux should not have any effect on the motion of particles in terms of classical mechanics. But as you know, if you go to quantum mechanics, then this phi does affect the motion of particles, even though it does not touch the particles directly. So in so quantum mechanically, we need to express this magnetic flux in terms of vector potential, because so Hamiltonian for single particle would contain this kinetic term, but this should be modified. And this A is a vector potential. And magnetic field is related to vector potential by rotation of A should match the magnetic field. And in quantum mechanics, you can identify the momentum as minus IH of derivative. So introducing this vector potential means that you had this momentum, and you replace this with minus IH bar nabla. So it means that so you basically replace the derivative by this so-called covariant derivative. And yeah, of course, this Q is a charge of the particle. So as you know, this electromagnetism is simplest and maybe most important example of gauge theory. So this means that in the presence of electromagnetic field or vector potential, when you consider parallel transport of wave function, usually you just translate the value of wave function to some neighboring location. But in the presence of vector potential, you need to change the phase of wave function according to the vector potential. So when you have some wave function and do the parallel transport, so when you want to change the location by delta r, you need to add this phase factor. Determined by vector potential. Okay, maybe I'm wrong with the sign, but anyway. So you need, when you parallel transport a wave function, you need to add this vector potential, phase factor, which depend on the vector potential. That's the role of the gauge field. So then, so even for this magnetic flux completely confined in the whole of the system, which does not touch the particles directly, you need to introduce a vector potential to represent this magnetic flux. So AX, so to represent this flux as I introduced, then because I chose this direction as X, so we need to introduce a X component of vector potential, which is 5 over Lx. Then so we have this kind of system, and when the particle propagates from here to there, you can move like this, or you can move the other way and end up at the same point. But because of this effect in the presence of vector potential, the quantum mechanical particle gains a different phase, whether you go this way or that way. So this will be more clearly formulated in terms of path integral, but I skipped the detailed formulation. But as you know, so for these two different passes, you get the extra phase difference. which is ax to the distance in x direction on this way and this way. That is, if you subtract the total length is Lx, so the difference in phase factor is nothing but this. So this is nothing but flux. So if you have, maybe I still want to keep the unit, then because of this, I should have so for magnetic flux phi, you get a phase difference for wave function if you go this way or that way. And this phase difference causes a different interference pattern. So in general, non-zero magnetic flux, even though this does not have any effect classically, has some effect on particle motion confined on this two-dimensional system. So this is the famous Aharonov-Bohm effect. So this effect only appears in quantum mechanical system. But from this, you can also see that there is a special value of the magnetic flux for which, so even when the magnetic flux is non-zero, under some circumstances, this Aharonov-Bohm effect vanishes. That is, so when the system is made of some elemental particles like electrons, then all the charges of microscopic particles or microscopic excitations should be integral multiple of elemental charge E. So if system like electron of charge E, then all the charges Q appearing in microscopic Hamiltonians are integral multiple of E. So in that case, so in this case, if phi is integer times phi 0, and phi 0 is 2 pi h bar over E, and 2 pi h bar is nothing but the original Planck constant h. So if your magnetic flux, Aharonov-Bohm flux, is integral multiple of this phi 0, which is sometimes called unit flux quantum, then this phase difference caused by magnetic field, which was a source of Aharonov effect, actually becomes integral multiple of 2 pi. So, but phase 2 pi is not observable. So phase difference 2 pi is identical to phase difference 0. So in this case, there is no AB effect. So such a magnetic field does not have any effect on the particle motion on this two-dimensional system. So this has several consequences. So for example, if you are studying a many particle system, then one thing you want to do usually is to obtain the energy spectrum, the spectrum of many body Hamiltonian. Then because of the AB effect, the spectrum generally depends on the magnetic flux. So let's say this is energy, and you have a ground state, and the first excited state, second excited state, and so on. And let's say this is a spectrum at phi equals 0. But when you insert this flux, then because of this AB effect, the particle motions are affected. So that means that these energy eigenvalues of many body Hamiltonian generally depends on phi. So maybe it changes like this, some dependence. But when you increase the flux and reach this value, phi 0, the unit flux quantum, then as I emphasized, there should be no AB effect because all the phase differences caused by magnetic flux becomes 2 pi times integer, which is not observable. So even though for generic phi, there is some dependence, but okay, so actually what happens in the middle is non-trivial question which I want to discuss. But in the end, if you come back to this particular value, then the spectrum should be completely identical to the spectrum at phi equals 0. So these two must be identical. These two must be identical. So this is a consequence of the absence of AB effect for the unit flux quantum. So this so in other words, if you are living on this two-dimensional system surrounding magnetic flux, then you can never detect the unit flux quantum inside a hole. So if it's a fractional, if your magnetic flux is a fraction of unit flux quantum, then you can detect this magnetic flux. which is actually experimentally done. But the integral multiple of unit flux quantum, you can never detect if you just live on the two-dimensional system surrounding the hole. And one of the consequences of this absence of AB effect is the identical energy spectrum. So then it might look tempting to associate the Hamiltonian at unit flux quantum and the Hamiltonian with zero flux. So if the Hamiltonians are the same, then spectrum must be the same. But actually, this obviously does not hold because this has non-zero vector potential. But this has zero vector potential. And whether you consider continuum system or system on lattice, non-zero vector potential and zero vector potential gives you different Hamiltonian. So this identity doesn't hold, but still the spectrum must be identical. And this is actually resolved in terms of the gauge invariance. So you can say that this phi equals to phi 0 and phi equals 0 represent the same physical system as far as this two-dimensional system is concerned. So they are gauge equivalent. So they are related by gauge transformation, but somewhat non-trivial gauge transformation, actually topologically non-trivial gauge transformation. Yeah.
So if I translate around closed loop,
Mm-hmm.
then I should always get a multiple of phi.
Yeah.
For the function.
Yeah. Yeah.
Are we making sure of that?
So
we translate around a closed loop.
Yeah.
So we end up back when we started.
Yeah, yeah.
Are we sure that in this case the phase difference will always be a multiple of phi?
Right, yeah. As long as the flux is integral multiple of this phi 0. Yeah. Of course, if you have generic value of phi, then you will get non-trivial phase. So very roughly speaking, usually the gauge transformation is formation is like if you have single particle wave function, you add some position dependent phase factor. So this is a usual gauge transformation. And usually this theta is a single valued function of location. But in order to eliminate this unit flux quantum, this gauge transformation should be topologically non-trivial. That is, when you go around the system, so you can write the gauge transformation in this way, but now the phase factor should be proportional to the x coordinate. So this phase factor should be like this. So that means that when you go around the system once, this x increases from 0 to Lx, so that this phase factor changes from 0 to 2 pi. So that this phase theta is no longer a single valued function, but what matters is the phase factor. So when you go around the system once, this phase increases by 2 pi, but the phase factor becomes 1. So this is still consistent with periodic boundary condition. So for single particle wave function, we want to do something like this. And for many particle system, we can also generalize this. So we can define a unitary operator, which is, yeah, for simplicity, I'm using the example of lattice model, but you can also define similar operator for system in the continuum space. So this is a operator which gives you large gauge transformation for many particle system. And this NR is number operator. At lattice side R, and this R consists of X, Y for two-dimensional system, and this X is the X coordinate of this location R. So basically, this corresponds to this phase for this phase for gauge transformation. And if you apply this, you can check that you can indeed eliminate the uniform vector potential, which corresponds to the unit flux quantum. Okay, so now that we have a large gauge transformation operator, we can relate Hamiltonian at zero flux with Hamiltonian at unit flux quantum. Yeah, maybe again, maybe I'm wrong with the sign, but doesn't matter much. So this means that these two Hamiltonians are unitarily equivalent, which explains that the spectrum must be identical, although they are different as operators, they are different. Okay. So this is called a large gauge invariance. Because as I said, the system with unit flux quantum and the system with zero flux are equivalent, because if you are living on this two-dimensional system, you can never detect the flux inside. And this equivalence is mathematically represented by this relation. So these two Hamiltonians are related by gauge transformation, but kind of topologically non-trivial gauge transformation, which is called large gauge transformation, which may not be the best name. Okay, it's not large versus small. It's more like a topologically non-trivial versus topologically trivial. But anyway, that became the standard name. So I just follow the standard terminology. Then I want to apply this large gauge invariance between zero flux state and phi zero flux unit flux quantum state to obtain various statements. So in order to do so, yeah, again, let's come back to the spectrum of this quantum many-body system. And we can classify quantum many-body system first by looking at the spectrum. So very broadly, quantum many-body system can be classified into two very broad classes. That is gapped system and gapless system. So this is classified into gapped and gapless. And as the name suggests, this classification is related to the energy spectrum. That is, you have energy eigenvalue, and you always have a ground state. And yeah, by quantum many-body system, I'm interested in, at least eventually, in the Sumner limit, the infinite system size limit. Then there must be infinite number of energy eigenstates. And basically, they form the continuum in the energy spectrum, continuum of the energy spectrum. But in some quantum many-body systems, the continuum of excited states starts, let's say, from here. So then above this, there is a continuum. By continuum, I mean continuum in Sumner limit. So for finite size system, each energy level is, of course, discrete. But if you take Sumner limit, they form continuum. But in some quantum many-body system, this continuum is separated from the ground state by some non-vanishing amount, which is called energy gap, excitation gap. So if this gap is non-vanishing, that is positive, then this system is called gapped. And the other class of system is you have ground state, and just above the ground state, you find a continuum. So which is, in this case, the system is called gapless. And very roughly speaking, for example, if you have insulator, okay, so as you might, maybe I will discuss later, but the conduction property of the system is not quite identical to this energy spectrum. So the relation is rather complicated or non-trivial. But at least very roughly speaking, the gapped phase corresponds to insulator, and conducting system like metals should correspond to this gapless state, because if you have good conductor, then applying just infinitesimal electric field, then the system should start carrying the current, which means that you can excite the system with infinitesimal energy. So that corresponds to gapless state. But if you are insulator, then you have to apply sufficiently large electric field to produce electric current, which means that the ground state is more stable or robust against external perturbation, which means that it's protected by gaps. So basically, you need to give system energy more than this gap to create any excitation. Although, as I said, the relation to conduction property is rather non-trivial, but that's a very rough understanding. So very roughly speaking, insulator should correspond to this. Conductor should be gapless. Then let me first consider this gapped system. And yeah. Mm-hmm. No. So up to this point, this can apply to any dimension, one plus one or more. I'm just applying vector potential in one particular direction. But so, for example, on the blackboard, I try to draw a two-dimensional system, but wrap at least one direction, x direction, impose periodic boundary condition. And for discussion up to this point, it's enough to impose periodic boundary condition in x direction and insert corresponding flux. But there is also y direction, and if you like, you can apply same argument to three-dimensional or four-dimensional system. Yeah. In one, yeah, one. Mm-hmm.
Like here is the C1, which is the
right. But yeah, later I want to thread the flux in different direction, but so far just in one direction. So yeah, first I consider this gap system. And well, usually we discuss this presence of gap or not at zero flux. And then I insert a flux. Then as I emphasized, if you come to this unit flux quantum, then the spectrum should be identical to the original phi equals 0. But for intermediate value of phi, this ground state energy will change, and also excited state energy will change. So in general, I don't know what happens on the energy spectrum in between this phi equals 0 and phi equals to phi 0. But I want to make a assumption, which is probably physically reasonable, although I think so far we have never been able to prove that mathematically. That is, if you start with a gap system, then as I said, the ground state is somehow stable. You need to give finite energy to create any excitation. Then if you have a gap, then this gap does not close throughout this flux threading process. That's the assumption. So this is reasonable if you consider someone. So eventually, as I said, I'm interested in sum-time limit. And in the sum-time limit, Lx goes to infinity, then the vector potential, the local value of vector potential becomes small, order of 1 over Lx. So especially when the system has a gap, then the ground state is kind of stable. So it would be reasonable to expect that this gap does not collapse for intermediate value of magnetic flux. Although, as I said, as far as I know, this has not been proven rigorously. But for short-range interacting system, this is perhaps a physically reasonable assumption. Then so if this assumption is true, if we accept this assumption, then if we insert this AB flux adiabatically, that is sufficiently slowly, so we start from, let's say, the ground state at phi equals 0, and then we start from the ground state at phi equals 0. Then if the gap does not close, and because at phi equals to phi 0, we come back to the original spectrum. So starting from the ground state, you must end up with the ground state. So this is just a consequence of adiabatic theorem. If the gap is always open, and if you change the parameter, in this case flux, very, very slowly, then you just follow the ground state. So if you start from the ground state, then after insertion of unit flux quantum, you must end up with the ground state. That's the adiabatic theorem. But interesting point is that sometimes we can show that you cannot just come back to the original state. So the initial state and final state must be different in some under certain condition. Then we can reach the non-trivial statement. So if this happens, then this contradicts with the simple assumption that you had the ground state and all the excitations had are separated by gap. So then, well, of course, one possibility is that this assumption is wrong. But if you accept this assumption that the gap never closes, then the possibility is that the system may be actually gapless, or there is still a gap, but there may be multiple ground states. So in this case, the system is actually gapless, or gapped, but with multiple degenerate ground state. So if this happens, then what we can rule out is the simplest possibility that if there is a single ground state, unique ground state separated from other excited state with a gap, then that scenario contradicts with this final state not being equal to initial state. So this last possibility, which is kind of most trivial scenario, can be ruled out if we can show that the final state must be somehow different from the initial state. And I'm going to discuss few examples where we can show this explicitly. Then we can show that either the system is actually gapless or the system must have degenerate multiple ground states if there is a gap. So that's a strategy. Yeah.
What was this unproved assumption? There seems to be two different statements. I'm not sure which one is the proven one and which one is the unproven. Is it that when I thread, when I change my boundary conditions, then the gap, if it doesn't already close, it will not close? Is that the unstated assumption? Or is it that if the gap is done zero, then
Oh, okay. So assumption is that if the gap is non-zero at, let's say, phi equals 0, then it's always non-zero between.
Have like a single state coming down and exchanging with the ground state or something like that?
Yeah, in principle, it's possible, but if you have many body Hamiltonian with short range interaction, and you have some gap between the ground state and the excited state, then my argument is that it's unlikely that the excited state comes down to the ground state. Of course, as I said, I have no mathematical proof, but it's kind of reasonable. And as far as I know, there is no known counterexample to this statement, because it's related to the robustness of the many-body ground state.
How come it's not can be compatible with the two possibilities?
How the assumption becomes compatible with these two?
Yeah, the gap, then obviously it's not gapless.
Well, yeah, more precisely, the assumption says that if the gap is non-zero at phi equals 0, then it's non-vanishing all the way to phi equals to phi 0. That's the assumption. So if the gap is 0 at phi equals 0, then it means that the system was actually gapless. Yeah.
So the assumption is only useful for the second possibility.
Kind of, yeah. Yeah, of course, if the system is actually gapless, then of course we don't need to assume anything like this, but it's always a possibility.
Yeah, so at least on a quantum, if you just take a particle in a circle and you dial the flux through a circle from 0 to pi or something, then there you do get a level crossing in the spectrum, right? So does that, so you're saying that cannot happen in a many-body system?
Yeah, many-body system with gap. So that simple example actually corresponds to the gapless system, because it's like a non-relativistic particle, for example, on the ring, which has quantized energy levels for finite size system. But if you go to, the summary limit, then the energy spacing becomes 0. That corresponds to gapless system in this. Okay. So as a first application, I want to discuss the consequence of so-called fractionalization. So by fractionalization, yeah, there are already known examples, like in quantum Hall state, Laflin state, for example. That is, you find a fractional charge in unit of elementary charge of electron, like 1/3 of elementary charge E. And people already experimentally found those fractionally charged excitations. And most naively, 1/3 of electron charge sounds like you have an electron, and you hit this electron with some hammer or something, and then electron is split into 3 parts. Then each part of electron carries 1/3 charge. But of course, that's not happening at least in condensed matter physics. And so far, we don't find any internal structure of electron. So up to the energy produced possibly by human civilization, you cannot really split electron into 3 pieces. But still in quantum Hall system, fractional quantum Hall states, people found 1/3 charge of electron, which means that it's not like splitting single electron into 3 parts, but you have collective excitation of many, many electrons. And those collective excitation can carry 1/3 charge. So those collective excitations are often called quasi-particle. So in general, fractionalization means that you have a system consists of elementary particle or constituent particle like electron with charge E. And there is no microscopic element which has fractions of this charge. So this is unit charge for every microscopic constituent. But still, you may have elemental excitation, that's a collective excitation of many particles, which has fractions of this charge. But yeah. Elementary. Okay, maybe I should have avoided the wording of elementary particle because I want to discuss elementary excitation, but this has very different meaning. So these elementary excitations are like a collective excitation. And which we can call quasi-particle with some fractional charge E star. And let's assume that there is also quasi-pole with opposite charge. And I assume that these quasi-particles and quasi-holes, how say, well, really behaves like a quasi-particle and holes. That is, they are not like fractons, which you cannot move. But these quasi-particles and holes, you can move around by, for example, adding appropriate potential and drag the potential, then you can drag the quasi-particle and hole around. That's our assumption. Then we can consider the process that you have this, let's say, two-dimensional system, and you create the quasi-particle and the quasi-hole pair by hitting the system. So initially the system was in the ground state. Then you introduce some potential perturbation or something, then create quasi-particle hole pair. Then move this quasi-particle around. And maybe you can move quasi-hole to the opposite direction. And when they meet, you can pair annihilate this quasi-particle and hole. Then after annihilating this quasi-particle and hole pair, you go back into the ground state. So let's denote this process as Lx. This consists of quasi-particle, quasi-hole pair creation. And then drag them around like this. Then you pair annihilate. Yeah, somehow this is getting heavier. Okay. Then I also want to do this adiabatic flux insertion as I discussed. So you can introduce flux like this. So this fx is a adiabatic from zero flux to unit flux quantum. Then, so this Lx creates a quasi-particle Hall pair, but you drag them around and you annihilate them in pair. So you must go back to the ground state. And also adiabatic flux insertion. Oh, and sorry, I forgot to assume that this system I assume to have a gap, and quasi-particle quasi-Hall's elementary excitation about the gap. Sorry, I forgot to assume. So I assume the system has a gap, and the quasi-particle and quasi-Hall's excitation about the gap. So then both of these Lx and Fx should bring ground state back to the ground state. But now the interesting thing happens. That is, you try to apply Lx after applying this Fx to the ground state. Then this Fx introduces the unit flux quantum to the system. So after applying this Fx, you have unit flux quantum. And I emphasize that this unit flux quantum is value of flux such that there is no Aharonov phase, Aharonov effect. So there should be no effect. But that argument was only valid for elementary charge particle like an electron, because phi 0 was defined like a Planck constant over E, and E was the charge of the elementary charge of electron. But in this Lx, actually, you create a quasi-particle and quasi-Hall pair and drag them around, and they are assumed to have fractional charge. And now fractional charge can fill this unit flux quantum. So quasi-particle, quasi-Hall can fill phi 0. Because now the phase difference caused by this magnetic field is E star over E times 2 pi. And if I assume E star was P over Q, some rational number times E, then this is 2 pi times P over Q. So, okay, so I'm running out of time. So let me finish this morning by giving you the final statement. And in the afternoon, I will give you a bit more careful treatment of this. But very roughly speaking, this means that Lx and Fx does not commute, because if you do this Lx after inserting the flux, you get this extra phase. So this means that roughly speaking, if you apply Lx after Fx, this produces different phase from applying first Lx and Fx, because if you do this, then you move quasi-particle with zero background. So you don't have extra phase coming from this AB phase. But if you apply Fx first, then you have a unit flux quantum, which induces non-trivial Aharonov-Bohm effect for quasi-particles, although not for original electron. So which means that you have some extra phase like this. And I assume that so if the system is gapped, then we expect both Fx and Lx should map ground state back to the ground state. But if you have only one ground state, then you cannot satisfy this relation, because each of them maps the ground state back to the ground state. Then if you have just one ground state, then you cannot have this relation. So this means that you must have multiple ground state. And we can show that actually there must be at least Q degenerate ground state. So which means that if you want to have fractionalization in that sense, having fractionally charged quasi-particle excitations out of the microscopic Hamiltonian, which consists of only charged E particle like an electron, then your ground state must be at least Q-fold degenerate. And we can also show that this must be so-called topological degeneracy. But yeah, I'm running out of time, so running over the time. So I stop here, and I will give slightly more careful treatment of this one, and discuss why this must be topological degeneracy, and also other applications like Luttinger in the afternoon. Thank you very much.
It was crystal clear for everybody. Questions?
Can I ask? So how do you know that LF and FL is only different by a phase? One would expect in general that they map ground state to different ground states.
Mm-hmm.
So how do we know that they're just a phase difference?
Yeah, so because, okay, so maybe in the afternoon I will give you a little bit more careful treatment, but basically these Lx are done with the background of this non-zero flux, phi zero, and this Lx is done in presence of zero vector potential. So the argument is that the only difference between these two comes from Aharonov-Bohm phase, which entirely comes from this parallel transport effect of wave function. So yeah, and also I should say that this relation is limited to the ground state subspace of entire Hilbert space. So actually, this is not operator identity. So you need to project this down to the ground state subspace. Then this should hold. That's yeah. Of course, this is not quite mathematically rigorous formulation. So there are many hand waving part, but at least this difference we can associate this difference only to the Aharon phase caused by this flux. So then the difference must be this AB phase. That's the argument.
When you say that you drag the particle, it means that you hook up a unitary operator.
Yeah.
Is able to do it.
Right. So So okay. So in the afternoon, I will give you a bit more precise version, but I'm assuming that there must be some time evolution process for some Hamiltonian with local perturbation, like a local potential. And under the time evolution, you can, for example, add a potential, positive potential, negative potential, which traps this quasi-particle hole. Then if you move these potentials slowly, then you can realize this process. That's the assumption. And then, we can show that, we can argue that this time-dependent process should be defined with respect to some time-dependent Hamiltonian. But those time-dependent Hamiltonians can be completely defined with respect to the microscopic degree of freedom, like electron. Yeah, that's the fundamental assumption.
And you're also assuming that this perturbation allows you to move the particles?
Yeah.
It doesn't close the gap.
Right. Well, okay. So by creating this, you are already at the excited state. But yeah, okay. I'm assuming that there is no other adverse effect. Yeah, okay. So there are a lot of hand wavings, but I would say that when we talk about quasi-particles and quasi-holes, in physics, we are implicitly assuming many properties like this. So it's mathematically very, very hard to formulate precisely. But when we talk about quasi-particle excitations in physics, I think we implicitly are assuming many assumptions like this.
When you introduced this large gauge transformations and this unitary operator, it seemed like it was generated by the dipole moment of the system.
Yeah.
Is there any relation to like dipole symmetries? Because those are global symmetries.
Yeah, so I hope I can come to that subject maybe tomorrow, but indeed this large gauge transformation operator is related to the polarization. So in fact, there is a Lester formulation of electric polarization, which is nothing but the expectation value of this unitary operator. Although I think in his papers, he never discussed this large gauge transformation, blah, blah, blah. So he arrived at the same expression from very different lines of argument, but basically he discusses the same operator. So yeah, this is indeed very closely related with electric polarization, which I hope I can discuss maybe tomorrow. Yeah.
And apply this argument to arbitrary dimension. Because it seems like assuming you are using U1 flux trading, then the structure of the chain class is the C1 or mechanical, this type of things exists in even dimension space-time only. So are you assuming possible different type of anomaly structure when you apply to other dimensions other than just having the U1 symmetry? Maybe you assume maybe some other things you're probing?
Well, maybe we should discuss in person, but so for me, even if I'm dealing with 2+1D system like this, I just wrap one direction and put the magnetic flux, and you can also impose periodic boundary condition in y direction, then impose a flux. So how to say? You can compactify d-dimensional D plus one dimensional system and a D dimensional spatial degree of freedom compactify into torus, then torus, D dimensional torus has D, non-trivial cycles, and for each of them, I can apply this argument. So I don't quite see the difference between even and odd dimension, but maybe we can.
Some people want coffee.